Buddies, this is Sidhu, Senior Lecturer in Chemistry from Sri Chaitanya Educational Institutions, Gosala. Today we are discussing about an important topic in chemistry NEET, that is chemical equilibrium. In fact, this topic is divided into two parts. One is chemical equilibrium and another one is ionic equilibrium. So now we shall discuss some important questions and models in chemical equilibrium. So shall we move forward? Let's go. Look at the first question is about the characteristics of chemical equilibrium, and let's see the question. For the equilibrium, which is A is in equilibrium with B, the variation of rate of forward reaction A and reverse reaction B with the time is given by, and we know that at equilibrium the rate of forward reaction is equal to rate of backward reaction. Here the rate of forward reaction initially is so high such that here it starts from the peak, and then the rate of backward reaction is almost zero at the beginning, therefore it has to start from the origin. So that means obviously A should be the peak and B should start from the origin. So therefore maybe if you see all these options, they are like same only, but the point is, as the equilibrium is approaching, as the time is going on, the forward rate decreases and backward rate increases. At equilibrium both rate becomes equal. If you see the graph, obviously look at there, option B. If you see here, at equilibrium both forward rate and backward rate becomes equal. Therefore what is the right answer? Right option, that is B. So this is the simple question, and we can expect this in NEET also, because the graphs maybe they are little confusing, but that you keep in mind. At equilibrium, rate of forward reaction and rate of backward reaction becomes equal. Let's go for the next question. This question is also about characteristics of chemical equilibrium. It is a theoretical question. Let's see the statements what are mentioned here. Here they have mentioned at equilibrium the vapor pressure of solution and refractive index of equilibrium mixture becomes constant. Let's see the next. Equilibrium can be attained in both homogeneous and heterogeneous reaction. Next statement. Approach to the equilibrium is fast in the initial state and gradually decreases. And fourth statement, equilibrium is dynamic in nature. So let's see the statement once again. As we know that at equilibrium almost all physical constants, almost all physical characteristics and chemical characteristics becomes constant. At equilibrium there is no change in volume, there is no change in concentration, there is no change in pressure. Like that only, there is no change in vapor pressure of a solution, and there is no change in the refractive index of the equilibrium mixture. First statement is right. Second statement, if you go for, equilibrium can be attained in both homogeneous and heterogeneous reaction. Obviously equilibrium can be attained in both homogeneous phase as well as heterogeneous phase. Let's go for third question, third statement. Approach to the equilibrium is fast in the initial state. Obviously initially the rate of forward reaction decreases that we discussed, and rate of backward reaction increases as we discussed in the previous question. So that means initially the approach is very fast, and once it is reaching equilibrium position, the reactions becomes, the rates become slow, such that here the approach, at the initial state it is fast and gradually it decreases. And then equilibrium is dynamic in nature. It is well known statement for us. So it seems that all options are correct. Yes, the actual answer is all options are correct, and then the correct option is D. All are correct statements. Let's go for the next question. This is about physical equilibrium. This question is about physical equilibrium. Let us see the question. Choose the incorrect statement involving equilibrium in physical process from the following. Look at option A. Equilibrium is possible only in a closed system at a given temperature. If you remember, in physical equilibrium we discussed, suppose a liquid is converting into a gas or vapor. When you open the container, the vapor goes away. That means the product is removed from the equilibrium mixture, such that how can we expect an equilibrium there? Therefore Equilibrium is attained in closed vessels or closed containers. Right statement. Option A is right. Let's go for next. Both opposing process occur at the same rate. This is also repeated like the first question only. At equilibrium, the rate of forward reaction equal to rate of backward reaction. Suppose if you take evaporation of a liquid, the rate of evaporation should be equal to rate of condensation. Now go for option B is correct. Now let's go for option C. When equilibrium is attained at a given temperature, the value of all its parameters become equal. This is a little tricky, so you must have patience to understand the statement. When equilibrium is attained at a given temperature, the value of all its parameters become equal. So what is the meaning of it? As we know that at equilibrium there is no change in concentration, there is no change in the pressure, volume and so on. We have seen many characteristics. Here they have mentioned it's not that they are constant. They are mentioning all the parameters become equal. That means actually there is a fault in the statement. Let's see the D also, then we will go for the right answer. Now for dissolution of solids in liquids, the solubility is constant at a given temperature. Obviously it is also a physical equilibrium. Dissolution of solids in a liquids at equilibrium, the solubility is a constant value. So option D is also correct. The only one option that is looking inappropriate is option C. At equilibrium it is not all parameters become equal. It is all parameters generally become constant. So that is the right way of framing the statement. Therefore the incorrect statement is option C. Let's go for the next question. This is a numerical based on the equilibrium constant value. So here let us see the equation, that is ammonium hydrogen sulfide solid is decomposing to ammonia and H2S gas. Ammonia gas and H2S gas. Since here it is in a heterogeneous equilibrium, as we know that for solids at equilibrium the activity is taken to be 1. For example, here how to write equilibrium expression for this? Kp is equal to, now what are the gases involved in the product side? Ammonia, I am writing the partial pressures. So the partial pressure of ammonia and partial pressure of H2S. This is the Kp expression. Now can we write the partial pressure of ammonium hydrogen sulfide? No, because here first of all it is a pure solid. Its activity is taken to be 1. What is the meaning of activity is 1 here? We can say that here the pressure exerted by the solid is actually taken to be unity or 1, because we can say that the pressure exerted by the solids compared to the gaseous is negligible. So therefore we are taking its active mass as 1. Also its concentration, it does not change with time. Therefore for pure solids the active mass is taken to be 1. Therefore I am not writing the ammonium hydrogen sulfide in the expression. So after writing this, what to do? Look at the question. The equilibrium pressure is 0.660 atmospheres. Then what is the Kp for the reaction? This looks a little tricky. They have given total pressure at the equilibrium. One thing that we know that in this equilibrium, if 1 mole of ammonia is formed, obviously 1 mole of H2S is formed. Let us take ammonia pressure is x atmospheres. Obviously the H2S pressure also becomes x atmospheres. So both become same value. So that is the very important point that you need to know to solve this problem. Since both pressures become equal, then what is the total pressure? Equilibrium pressure, that is equal to x exerted by ammonia and x exerted by H2S. Therefore x plus x become 2x. Obviously. So what is this 2x value? The 2x value is how much? They have mentioned it as 0.660 atmospheres. 0.660 atmospheres. I hope you got this point. Yes or no, friends? Do look at here. Ammonia, if it exert x atmospheric pressure, H2S also exert the x atmospheric pressure. That means here both are equivalent in amount at equilibrium. That is the key point to solve the problem. How, sir? Because the ratio, you see, mole ratio 1:1. What about ammonium hydrogen sulfide? That does not require for us, because ammonium hydrogen sulfide is a solid, its pressure is taken to be Okay, 1, or actually we can neglect it, sorry, here we can neglect it. Unit active mass is 1. Now only ammonia and H2S are there, and they are in 1:1 ratio. Therefore their pressures becomes x atmosphere if you take. What is the total pressure at equilibrium? X plus x, 2x, that is 0.660 atmosphere. Then what is x value? That is pressure of ammonia, that is 0.660 divided by 2, that value becomes 0.33 atmospheres. Now we have got the pressure of ammonia as 0.33 atmosphere, that is x, and the pressure of H2S as 0.33 atmosphere, that is also x. Therefore, if you take the equilibrium expression now, if you substitute here, what is the pressure of ammonia? X. What is the value? 0.33. What is the pressure of H2S? X. What is its value? 0.33. Now, what is 0.33 into 0.33? That is approximately, okay, it is close to, say, 1 by 3 can we take? 1 by 3 into 1 by 3 is 1 by 9. 1 by 9 is approximately, we can say, 0.109. So, what is the right answer? The right answer is option A, 0.109 atmosphere square. I hope you are clear with this. What is the key point in this problem? The key point in this problem is the ratios of ammonia and H2S are same, 1:1 ratio. Therefore, we are taking their pressures are equal, x and x. And then if equilibrium pressure is 2x, the total, then we got the pressure of ammonia and pressure of H2S, and then we write the equilibrium expression, and then we got the answer 0.109 0.109, sorry, 0.109 atmosphere square. That's all. Let's go for the next question. Yeah, next question is also a numerical based on the equilibrium constant. So let's go for the question once. 1 mole of dinitrogen tetroxide, 1 mole of dinitrogen tetroxide at 300 Kelvin is kept in a closed container at 1 atmospheric pressure, and then it is heated to 600 Kelvin. Again, please keep this in mind, it is heated to 600 Kelvin, and then when it is 20% dissociated. So upon heating, it is 20% dissociated. Then what is the final pressure or resultant pressure of the mixture? This involves, okay, an interesting and important law, that is gases, okay, among the gas laws that we know that pressure here directly proportional to number of moles. Here volume is constant, and here one more thing, temperature is changing, and also number of moles are changing. So if you apply the ideal gas equation that we know, it is related to equilibrium chapter only, but we have to know the basic principles of ideal gas equation. So PV is equal to nRT. Here volume is constant and R is constant. Pressure directly proportional to number of moles into temperature. So this is the principle that we need to use. So what is P1 initial pressure? What is P2 final pressure? What is N1 initial number of moles? What is T1 initial temperature? What is N2 final number of moles? What is T2 final temperature? That we know. So by using this principle, we can solve this problem. Now how to apply the chemical equilibrium here? The principles of chemical equilibrium here. Let me write the equation here once again. The equation here it is N2O4 gas is in equilibrium with 2NO2 gas. N2O4 gas is in equilibrium with 2NO2 gas. Let us take initially 1 mole is there. 1 mole is taken. And then what is the number of moles of this? 0. Now let us assume that x moles it is dissociated. Then what is the produced moles as per the stoichiometry? 2x moles. If x moles it is dissociated, 2x moles is produced. Why? Because 1 mole of N2O4 gives 2 moles of NO2. Okay, done. Then what is x? That we have to know. They have given the degree of or percentage of dissociation. What is percentage of x? That is 20%. Then what is x? How do we calculate? The percentage of dissociation divided by 100, that is 20 divided by 100, that is equal to 0.2. The degree of dissociation is 0.2 here. If you take 1 mole, here x moles it is dissociated, that means 20% of 1 mole. What is 20% of 1 mole? 0.2. That means x value we have got it as 0.2. Then what is this 2x value? 2 into 0.2, that is equal to 0.4. We have got it as 0.4. Then what is the final number of moles in the mixture. The final number of moles in the mixture is, we need to subtract, you know this in chemical equilibrium, I have seen this type of principles. This is 1 minus x, that is 1 minus 0.2, because 1 mole of N2O4 is taken and 0.2 moles is reacted. Then what is this? Total moles of N2O4 present is 0.8. Then what is the moles of NO2? 0.4. Then tell me, what is N1? What is N1 from here? What is N1 from here? What is N1? Let's write here. I am writing what is initial number of moles. 1 mole of N2O4. What is final number of moles? Final number of moles, it has N2O4 as well as NO2. What is N2O4 moles? 0.8. What is NO2 moles? 0.2. So what is the final number of moles at equilibrium? That will become 0.8 plus 0.4. So 0.8 plus 0.4 is how much we are going to get? 1.2. We have got it as 1.2. Now what is initial pressure? P1, 1 atmosphere. What is initial pressure? P1, 1 atmosphere. What is initial temperature? T1, 300. Sir, why to take temperature? So many of them do the mistake here. Here temperature also changing. Generally people do mistakes here only. They don't consider the temperature. So directly they go for pressure directly proportional to number of moles. There is one option also, we will see that. So here P2, that is a trap to you. We need to identify what is T2, that is equal to 600 Kelvin. Now if you substitute there, what happens? Let us see. If you substitute there, what happens? Let us see. P1 by P2 is equal to N1 T1 divided by N2 T2. So I am writing here the final answer. Do look at what is P1, 1 atmosphere. What is P2? We need to identify. What is N1? 1 mole. What is T1? 300 Kelvin. What is N2? 1.2. Okay. What is P2? That is, what is T2? Sorry, 600 Kelvin. Then what is P2? That is equal to, if you simplify this, 300 divided by 2, that is 2 into 1.2, 2.4 atmospheres we are going to get. 2.4 atmosphere we are going to get. This is the right answer, that is 2.4 atmospheres. So actually here, what is the mistake people do is, they don't consider the temperature. If you don't consider temperature, what happens to the answer? Suppose temperature is not considered. I don't take the 300, 600. Then simply P2 becomes 1.2 atmospheres, which is wrong. And check, we have the first option. We know the students are so in a hurry mode in the examination. They go for 1.2 atmosphere as the answer, and that is the first option. You are in a hurry mode, then go for the first option directly. Though please, I am warning you, here temperature also changed. Therefore, the actual answer is option B. The actual answer is option B, that is 2.4 atmospheres. I hope you are clear with this numerical. Now let's go for the next question, that is related to the calculation of equilibrium constant only. Look at the question. They have given the following concentrations were observed at 500 Kelvin for the formation of ammonia from nitrogen and hydrogen at equilibrium. And they have given the equilibrium concentrations, and then we need to identify the equilibrium constant value Kc. This looks easy. The only difference is here we need to do the numerical. It takes time, that's all. We know the formation of ammonia. Formation of ammonia, what is the process? Okay, what is the reaction? The Haber's process, that is N2 is in equilibrium with 3H2 and produces 2 ammonia. So this is the Haber's process equation. Now this is the formation of ammonia. Sir, why can't we take half NH3? We can why can't we take 1 mole of NH3, because they mentioned it is formation of ammonia. We can try that one also. First I am doing this trial and error. If I don't get that option, then I will see that half NH3 also. 1 mole of NH3 also. I will show that one also. Now let's go for that. Here what happens? Do look at here. What is the Kc expression for this problem? Kc expression for this problem is ammonia square, that we know. Ammonia square divided by N2, concentration of N2 and concentration of H2 cube. Concentration of ammonia square divided by concentration of N2 into concentration of H2 cube. Let's substitute the data. Let's substitute the data. Here be cautious when you substitute the data. So Kc is equal to, what is concentration of ammonia, friends? Concentration of ammonia is 1.5 into 10 power minus 2 molar whole square divided by concentration of N2 is 2 into 10 power minus 2 and concentration of H2 is 3 into 10 power minus 2 whole cube we are going to get. So this is the concentration. So after substitution, let's do this value. This is 1.5 square. I am separating the exponents and the pre-exponents. This is 2 and this is 3 cube. Then let's see the powers. 10 power minus 2 square, that is 10 power minus 4, and this is 10 power minus 2, and then we are going to get this is 10 power minus 6. Are you clear with this? Then we need to solve this further. 1.5 square, that is 2.25. 2 into 3 cube, that is 27. 2 into 27, 54. And then finally, after the powers, okay, exponents. So this is 10 power minus 4, this is 10 power minus 2 into 10 power minus 6, 10 power minus 8. If it goes up, finally we will get 10 power 4. 10 power minus 8 and 10 plus 8. Then power 4 we are going to get. Now we need to simplify this. So I am taking it as suppose 225 divided by 54 into 10 square. So obviously 54 approximately 4 times you will get, right? If you do this, you will get around 4.17 something. So 4.17 into 100, 10 square is how much? 4.17 into 10 square, that is approximately we will get 417 atmosphere. The point is, the answer is 417 atmosphere. The point is here, sir, for formation of ammonia we should take only 1 mole of ammonia. Then what happens is, here it should be half the equation. That means if you multiply this equation with half, it will be around root 417. Root 417 is not in the option, so therefore don't worry about that. So what is the right answer? Option A, 417. Let's go for the next question. Let's see one more question about equilibrium constant. This is also a numerical. For the given reaction, A is reacting with 2B to produce 2C and D. The initial concentration of B was 1.5 times that of A. At equilibrium, if the concentrations of both A and B are equal, then equilibrium constant K for the above reaction is. So let's write how to do this problem. So this is the equation A plus 2B, which is in equilibrium with 2C plus D. Let's take initial concentration of A as 1. We can take it, no issue with that. Initial concentration of A as 1 and then B as how much? 1.5. Generally you have a habit of taking 2 directly. No. As per the examiner's data, we need to move forward. For the given reaction, A is in equilibrium with 2B, but what it is mentioned, 1 mole of A is taken. If you take it, then concentration of B is 1.5 times that of A, means it is 1.5. We should not take it as 2. And what is the concentration of C and D? 0 and 0. Now let us take X moles of A is reacted, or X molar A is reacted, then 2X molar B is reacted. Sir, why can't it is 1.5 or 1.5X? No. Reaction should take place as per stoichiometry only. So 1 mole of A react with 2 moles of B, X moles of A react with 2X moles of B. Then it produces 2X moles of C and then X moles of D. I hope we are clear with this. Now what is remaining at equilibrium? 1 minus X of A and then 1.5 minus 2X of B, because here reactants react, therefore we need to subtract, and then 2X of C, because 0 plus 2X is 2X only. Why is our plus? Because the products are produced, therefore we need to add plus there, and then 0 plus X of, that is X. So that means we have got the equilibrium concentrations of A, B and C, D. Now what is the next point it is mentioned? Here the equilibrium concentrations of A and B are equal. That means they have given 1 minus X is equal to 1.5 minus 2X. Now if we rearrange it, what happens? We will get as 2X minus X is equal to 1.5 minus X. So finally, 1.5 minus 1. So what we will get is 1.5 minus 1. So what we'll get is, here it is x is equal to 0.5. We got the x value. Then what is concentration of A? The concentration of A is 1 minus x at equilibrium. 1 minus 0.5, that is equal to 0.5. Then what is concentration of B? That is equal to 1.5 minus 2x. We can directly write it is equal to, okay, but anyway I am writing 1.5 minus 2x. 1.5 minus 2x, that is 1.5 minus 2 into 0.5, that is equal to again 0.5. Then what is concentration of C? That is equal to 2x, that is 2 into 0.5, that is equal to 1.0. Concentration of D, that is x, that is 0.5. So we got everything. Then we need to write the Kc expression and tell the answer. So what is Kc expression? Let's write the Kc expression. The Kc expression is, if you go for the Kc expression, what happens is, because this concentration of C square, and I think let me write here. Okay, concentration of C square and plus into concentration of D divided by concentration of A, concentration of D square, B square, concentration of B square. If you substitute all the data, what happens? Let us see. Concentration of A is, okay, concentration of C is how much? It is 1 square. Concentration of D is 0.5. Concentration of A is how much? It is 0.5, and concentration of B is 0.5 square we are going to get. So therefore everything, if you solve it, what is the final answer? 0.5 got cancelled, and 1 by 0.5 square, that is 1 by 4. The final answer will be exactly 4. So what is the final answer of Kc? That is equal to 4. So A is the right answer. So let's go for the next question. Next question is very simple question that we know. There are well known questions about relationship between Kp and Kc. Now what is the relation, friends? If a chemical reaction is given, the relation between Kp and Kc is Kp is equal to Kc RT whole power delta Ng. What is this delta Ng? The delta Ng is number of moles of gaseous products minus number of moles of gaseous reactants. Number of moles of gaseous products minus number of moles of gaseous reactants. So they must be in gaseous state. They must be in gaseous state. Now how many moles of products are there in the above equation? 2 moles of NO2. So 2. How many moles of reactants are there? Only 1 mole of N2O4 gas, 1. Therefore what is the delta Ng? 1. Now what is Kp-Kc relation now? The Kp-Kc relation now it is Kp is equal to Kc into RT. Kp is equal to Kc into RT. Now they have given all the data, then we need to identify what is Kc. Kc is equal to Kp divided by RT. Now substitute the data. What is Kp value? 0.492. What is RT value? R value 0.082. What is the temperature they have mentioned? It is 300 Kelvin. If you substitute, what is the answer? Let's see. This is around 24 points something we will get. So 0.492 divided by 24.6 something we are going to get. So if you do that, here they have given 10 power minus 2, that you keep in mind. 10 power minus 2 as given. So therefore 10 power minus 2, if you take it, approximately it is 2. Okay, let me write. So what is the answer we are going to get? Let's see. Here if I take 10 power minus 2 as separated, then it will become 49.2, sorry. So we will get 49.2 into 10 power minus 2 divided by 24.6. So obviously it is 2 into 10 power minus 2. So what is the answer? 2, okay, option A, 2 into 10 power minus 2. Let's go for the next. This is 2. So this is also related to relationship between Kp and Kc. However, but it's not a numerical that we know. Look at the question. In which of the following equilibria Kp is not equal to Kc? First of all, when does Kp becomes Kc? So let me write the relation once. Kp Kc, or Kp is equal to Kc into RT power delta n. Suppose if delta Ng is 0, delta Ng, then what happens? Kp is equal to Kc. But they are not asking Kp should be equal to Kc. Kp should not be equal to Kc. Kp should not be equal to Kc. That means here delta Ng should not be equal to 0. Okay, now should not be equal to 0. Now let's see the options we have. Let's see the options we have. Look at the first option what we have got. In the first option, what is delta Ng? Write down the delta Ng here. How many moles of gaseous products are there? 2 CO. And how many moles of gaseous reactants are there? 1. 2 minus 1, that is 1. I think we got the answer. Let's go for next. 2Hi gas gives H2 gas and I2 gas. That means what is delta Ng here? How many moles of gaseous products? H2 gas and I2 gas. 1 plus 1, 2. How many moles of gaseous reactants? 2Hi. That means 2 minus 2, 0. Here if you go for the next question, delta Ng, next option, sorry. So here NO plus SO3, 1 plus 1, 2 moles and 1 plus 1, 2 moles. 2 minus 2, how much? 0. Let's go for next, N2 plus O2, 2 moles. And minus, this is 2NO2. Again, we are going to get 0. Therefore, what is the right answer? Delta Ng should not be equal to 0. Therefore, what is the right answer? It is option A. Let's go for the next question. The next question is about factors influencing the value of K equilibrium. Value of K equilibrium. It is not Dichat-Leer's principle. It is the value of K equilibrium. These are also well-known questions. If you change addition, subtraction, and if you do reversal of the equation, if you add two equations, these type of questions we have seen. Let's see one more type. The value of Kc is 60 for the above equation. This is 64 they are telling. The value of Kc. And the value of Kc for the following equation is, what is the relation between the first equation and second equation? If you see, they are in the first equation ammonia is formed, but in the second equation ammonia is actually reacting. It is reacting. That means we need to reverse the first equation. Okay, let me reverse the first equation. What will happen if I reverse the first equation? That means if you take 2NH3 is in equilibrium with N2 plus 3H2. If you reverse the equation, what happens to equilibrium constant value? That becomes reciprocation. That means the new Kc, I am taking as Kc bar, it will become 1 by 64. 1 by 64. This is the principle. When you reverse the equation, you will get equilibrium constant value as be reciprocated 1 by 64. Then what we need is, here 2 moles of ammonia is reacting, but we need only 1 mole of ammonia. That means we need to multiply the equation with half. That means I am multiplying the above equation with half. Then what happens? Half into 2, 1 mole, and then half into N2, okay, half N2, and then half into 3, that means 3 by 2 H2. We got it. So we got our equation, NH3 gas reacting with producing half N2 gas and 3 by 2 H2 gas. Now I am multiplying with half means what happened to our new equilibrium value? Suppose I am taking as Kc double bar, that is we are multiplying with half means this will become 1 by 64 whole power half. That means 1 by root 64 it will become. 1 by root 64 means how much it is? 1 by 8. So this is the answer. So what is the 1 by 8 answer? This is option A. So these are the problems, okay, where equilibrium constant value changes by if you do some addition, subtraction or reversal or multiplying with some value. Let's go for next. Let's go for next question. This question is related to the relation between Gibbs free energy and equilibrium constant. Look at the question. Consider the following reaction approaching equilibrium at 27 degrees Celsius and 1 atmospheric pressure. A plus B gives C plus D, where forward rate constant is 10 power 3 and backward rate constant is 10 power 2, 10 square. So then we need to identify the standard Gibbs free energy change. Now what is the relation between standard Gibbs free energy change and equilibrium constant? That we know. Delta G naught is equal to minus 2.303 RT log K equilibrium. Minus 2.303 RT log K equilibrium. This is the relation. This is the relation. Then what is K equilibrium value? The K equilibrium value we can write here, that is forward rate constant Kf by backward rate constant Kb. What is forward rate constant? 10 cube, backward rate constant 10 square. Then what is the value? We are getting it as 10. So forward rate constant is Kf 10 cube divided by backward rate constant 10 square. Therefore the value is 10. Now if you substitute the data, we will get the answer, but the answer should be in kilojoules. So let's see. I am substituting the data. So here this is minus 2.303. What is R value in joules? 8.314. What is temperature? 300. What is the equilibrium constant value? That is log, equilibrium constant value is 10, log 10 I am writing. As we know that, what is log 10 value? Log 10 value is 1. Therefore, the delta G0 value is equal to minus 2.303, R value 8.314, temperature 300, log 10 value 1. If you substitute or if you do this, we will get approximately, this is around 5750 joules. So let us convert this into kilojoules, approximately 5.75 kilojoules, that is the answer. So minus 5.75 kilojoules is the answer. So this is the relation between Gibbs free energy and K equilibrium problem. Let's go for the last topic in chemical equilibrium, the important topic, that is factors influencing equilibrium position. That is Le-Chatelier's principle. So look at the question in this. Consider the following equation. The 2 moles of sulfur dioxide is reacting with 1 mole of oxygen, produces 2 moles of SO3. The enthalpy change for the above reaction is as minus 190 kilojoules. The number of factors which will increase the yield of SO3 at equilibrium from the following is, they have given certain factors. So we need to identify the number of factors. What are those factors? Increasing temperature, increasing pressure, adding more SO2, adding O2, and addition of the catalyst. So these are the factors that are influencing the above equilibrium. So, but what we need is which will drive the reaction in forward direction, that gives more yield of SO3. Let us see the first question or first point or the first factor, that is increasing temperature. As we know that increasing temperature favors endothermic reaction. But what about this reaction? This reaction is exothermic or endothermic? Exothermic. Why it is exothermic? Because the temperature, delta H sign is negative. Delta H sign is negative. That means heat is released. It is an exothermic reaction. So increasing temperature favors forward reaction if it is endothermic. But here we are not. It is exothermic reaction. Therefore, backward reaction takes place. Backward reaction means more SO3 is produced. No. Backward reaction means less SO3 is produced. That means we reduce the yield. Therefore, we should not increase the temperature. Therefore, that is not the right choice. Let's go for next. Increasing pressure. As we know that increasing pressure favors more or less number of molecules, less number of gaseous molecules. Increase in pressure favors less number of gaseous molecules. Now, if you see the reactant side, how many gas molecules are there? 2 moles of SO3 and 1 mole of O2. If you see the reactant side, 2 moles of SO2 and 1 mole of O2. How many moles are there? 3 moles of reactants are there. Reactants are 3 moles, and here product side how many moles of SO3 is there? 2 moles. That means reactant side 3 moles are there. Product side how many moles are there? 2 moles are there. Reactant side 3 moles are there. Product side 2 moles are there. Increase in pressure favors less number of moles. Less number of moles is which side? That means in the product side. That means in the right direction. So in the product side, less number of moles are there. Therefore, we will get more product. What is our product here? SO3. Therefore, more yield of SO3 is produced when we increase the pressure. Let's go for next. That is adding more SO2. As we know, as per Le-Chatelier's principle, if you add some reactants, then equilibrium shifts in forward direction because rate of forward reaction increases. Adding reactants, either SO2 or O2, both cases, okay na, it makes the forward reaction better. That means, the yield of SO3 increases. Therefore, both are possible. Now, addition of catalyst. As we know that After reaching equilibrium position, there is no effect of the catalyst. Therefore, that is also not the right choice. Therefore, we have three options to increase the yield. Either increase the pressure or add the reactants. Also, we can remove SO3, but that's not in the options. So, therefore, what are the three choices we have? Increasing pressure, adding more SO2, adding more O2. That means here, what are the number of factors that influence, or what are the number of factors that influence to get good yield of SO3? That is option, and that means option A is correct answer. That is three options. I mean to say the three choices: increasing pressure, adding more SO2, and adding more O2. Let's go for the next question. The next question is also related to the same. Let us see the question first. Consider the following reaction. N2O4 is in equilibrium with 2NO2. It's an endothermic reaction. Delta H is plus 58 kilojoules. For each of the following cases, A and B, the direction in which side the equilibrium shifts. So, let's go for that. First of all, what is this reaction? This reaction is endothermic or exothermic? This reaction is endothermic. Delta H is positive. This reaction is endothermic. If it is an endothermic reaction, increase in temperature favors the endothermic reaction in forward direction. That means towards the product side. Increase in temperature favors an endothermic reaction towards forward direction. That means the product side. That means if we increase the temperature, the products are more produced. That means here, if temperature is increased, the products are more produced. But what it is given in option A, the temperature is decreased. That means exactly opposite you will get. So, the temperature is decreased here. That means instead of product side, which side the reaction shifts? That is towards the reactant side. That means A means towards the reactant side. Towards reactants. After that, we will see the options. A towards the reactant side. It is an endothermic reaction. So, increase in temperature favors the forward, the product side, but here they are decreasing the temperature. Therefore, it is backward. That means towards the reactant side, the equilibrium shifts. Next, pressure is increased by adding N2 at constant temperature. This is little beyond, okay, now your scope. Maybe it is not mentioned in NCERT, but previously they have asked in the AAPMT and other competitions for medical exams. So, now I am discussing this one also, addition of an inert gas. Okay, this is not related to N2O4 or NO2. N2 is a different gas. It is not, okay, either we are not adding reactant or we are not adding product, or we are not removing reactant or product. We are adding a new type of gas, which is inert gas. So, here, okay, now pressure is increased by adding N2 at constant temperature. Here temperature is constant, but pressure is increasing. That means what is the another one also constant? Here it is volume also constant. Here volume and temperature we are making constant, and we are just increasing the pressure by adding the number of moles. So, here if number of moles of gases are increased, pressure increases. PV is equal to nRT, P directly proportional to N here. So, what happened here I am discussing here, this is the ideal gas equation. PV is equal to nRT. Here we are keeping volume constant, temperature constant, and then here we are simply increasing the pressure. That means we are by how to increase the pressure? By keeping remaining constant by adding number of moles. What number of moles here? We are adding nitrogen, an additional inert gas we are adding. So, P directly proportional to N here. That means total pressure increases. Now, what happens if total pressure increases? Here, if you add an inert gas at constant volume, the total pressure increases, that we know. But what happens to the partial pressures of the gases? Here we are adding extra gas. That means here total moles also increased. So, total pressure increases, also total moles increases. I am telling total pressure increases, total moles increases. What is partial pressure? Partial pressure of a gas is, okay, the mole fraction of the gas into total pressure. Mole fraction of the gas is Ni divided by N total into P total. So, here total pressure increases, at the same time total moles also increases. That means on a whole no change in the partial pressure of the gas. No change in partial pressure of the gas. That means there is no effect. With B there is no effect. So, therefore, in case of A towards the reactant it moves. In case of B there is no effect. Therefore, what is the right answer? In case of A towards the reactant and in case of B there is no change. Therefore, what is the right answer? The answer is B. Okay. So let's go. So these are the important models that we have covered in case of chemical equilibrium. Thank you very much.